Okay, let's go through the MCQs. Okay, I know some of you are not done, but that's fine. Alright, as I'm going through, hopefully it will reignite some of your knowledge on the topics. Okay, this will serve as it's just a revision worksheet. Okay, it's supposed to be a mock paper. I'm supposed to give you guys a certain amount of time to do all the questions, but I feel like that's a bit counterproductive. So let me just go through bit by bit. Okay, MCQs first. Which set of quantities are all vectors? Your answer for this one is A. Okay, what is vector? Vector means you have magnitude and you have a direction. Okay. Of course, the opposite of vectors will be your scalars. Okay, scalar quantities only have magnitude. Okay, so let me just go through what's wrong with the others. Okay, this one and this one are scalar quantities. In fact, your power is also a scalar quantity. For GPE, again, energy is also scalar. Weight, pressure, and work. Work is a type of energy. So, again, he is a scalar quantity. Okay. Okay, but acceleration, displacement, velocity, all of them are vector quantities. You have to be going in a specific direction. AKA, the moment you have vector means there is a possibility that you can get negative values if you are going in the so-called wrong direction. Are we okay? Good? Okay, next. The figure below shows 3 force vectors. Okay, which one will likely represent the resultant force? Very easy question, just draw. 30 here, 40 here, you go back 10 a little bit. Okay, this is your final point, your end point. Okay, so your start from your start to your end, this fella is your resultant. So the answer is B. Are we okay? Can? Okay. Question 3. In the diagram, 2 steel cans X and Y with outer surface of different textures with the same amount of water heated at the same power. Which one of the following statements is correct? What? B. Water in X will boil faster because dull surface is a good absorber of radiation. Agree. Good. Okay. You these two. Yes, indeed, your polished chrome is poor absorber, polished chrome is a poor emitter. So why the fuck would you boil faster? It makes no sense. Yes? Okay, good. Question 4. The results obtained in an experiment to determine density of plastic material. What is the density of the plastic material? 4.5 grams. Volume. Wait, this is like a freaking primary school question, isn't it? Wait, is it? Sorry, let me just. Did anyone know how to do this? Okay, Kara, what's your answer? What's your answer? Oh, you don't know how to do. Why? This is mess. How to get volume? This thing by itself is you have 85 cm cube. If you add the plastic material, it becomes 103 cm cube. What's the volume of the plastic material? Right. 18. So you have 18 cm cube, 4.5 grams, 0.25 grams per cm cube. Yes. Why? Density is mass over volume. Are we okay? Okay, use this as a form of revision. Question 5. Stone is thrown upwards from the top of the cliff. After reaching maximum height, falls past the cliff and into does it. Vertical velocity after being thrown upwards. RNS is magnitude of the radius. Okay, what is the height? Okay, the answer for this one is R minus S, C. Okay, how are we going to do this? Okay, it's by visualization. Picture your ball. Okay, you are going to throw him upwards. At some point, he's going to hit his maximum height and he's going to start going downwards. Yes? Okay, it's just simple physics. So, when you throw him upwards, you will hit your maximum height here. Why is this the point of maximum height? You guys can start writing this if you don't know how to do. Okay, it's because your velocity changes direction. Can you guys see that it goes from positive to negative at this point? Okay, and the only reason for that is because I've hit my max, I'm starting to go down, I'm starting to fall. So your velocity change direction means you will have your maximum height. Next, as you are going to fall all the way here, this distance that you went upwards, where you went up first, is your S. Which means if I extend this line, I will also fall a S distance downwards, correct? Correct. Okay, and then you visualize the cliff. The cliff is like this. So what is the height of the cliff? This whole thing is R. So your height is your R minus the S. Correct? Because you went up S, your actual distance, right, is SSH. But in terms of the diagram, it's just S plus the whole R.
Wait, so R is from like the top of the cliff to like the sea?
No, R is from your maximum height to the bottom.
Or of the ball to the sea?
Correct.
Okay.
So if you just want the cliff, then you have to minus off your initial height and shoot it up. Following? Yes? Okay, good. Next. Displacement time graph. Which one shows decreasing velocity? Good? B. Agree. Okay, decreasing velocity. What is velocity? Velocity is rate of change of displacement. AKA is the gradient of your displacement time graph, of your dt graph. Okay, in the same way that acceleration is the gradient of your vt graph, velocity is the gradient of your dt graph. So if you have decreasing velocity, that means your gradient is getting more and more gentle. So just find a point where your gradient is getting gentler. Any questions? You okay? A man is in water of density 1000, he dives from point S to point T, aka he goes down by 4 meters. What is the change in pressure? Change in pressure, am I going to include atmospheric pressure? No, right? Because before and after both also atmospheric pressure, huh? So there is no change in that area. My change will come from these 4 meters worth of depth. Okay, pressure. I saw some of you writing P equals to F over A. Yes, pressure is force exerted per unit area. But you don't know how fat this fellow is, you don't have its area. So we have used another method. We have used rho times G times H. Density is 1000, G is 10. You went down a height of 4 meters. 40,000 Pascals is your answer. Jared, go ahead. You ready for it?
Rho is it?
Yes, rho is density. Any questions? Is it okay? Next, a lamina is suspended freely from point A. You are displacing it to a certain position. What is the moment due to force F about point A? Force F acts along this horizontal line here. Okay, in an exam, don't be afraid to just draw it over, it's the same. Okay, your perpendicular distance is S, so your answer is B. Easy? Force times perpendicular distance. Jaden? You get it? Good. Are you okay, question 8? Can I? Okay. Now, when a 0.2 kg brass cylinder is heated with a 2 kilowatt heater, its temperature increases from this much to this much in 3.2 seconds. What is the specific capacity? specific heat capacity, take a look at all your units, guys. Okay, joule per kg degree Celsius. Even if you forgot the formula, here is how we can derive the formula. Okay, it is energy per mass per change in temperature. Can you guys see that? Kg degree Celsius. Okay, right now, kg is mass, degree Celsius is fucking change temperature. Right? Okay, from this point, then I'm like, oh, okay, so if the unit of this is C, that means your energy is C times mass times change in temperature. Oops, and you free food. What's this? Okay, then we get our formula here. Math. What's what? C is, okay, I call it C because it's specific capacity. If you want to acronym it, you can just put SHC maybe. Specific capacity. I'm deriving the formula from the unit of the quantity. Okay, if you are fucking lazy to memorize the formula, which you shouldn't be, by the way, MC delta T, there's a certain rhythm to it. MC delta T, MC delta T, MC delta T. Just repeat it like 10 to 20 times, right?
Wait, so is C the unknown? Huh?
Exactly. C is the unknown. You are supposed to find it. Right? Yes.
So is it like below energy?
Mass, change in temperature. Right? Joules is energy. Kg is mass, degree Celsius is temperature. So once we have this, then we can derive our formula by bringing the mass and the T upwards. Huh? Yeah? Yeah or huh? Okay? Sure. Okay, what's my next step?
0.2 times 80.
0.2 times A. Oh, okay. So on the right side,
Yeah.
so okay, your specific heat capacity is your unknown, so I'll just put it at big X. Okay, 0.2 kg. What else?
Times 80.
Times 80. Very good. What's on the left side?
Energy.
Thank you. What is the energy?
Is it just 2?
Nope. What's this?
2000.
This is watt. What is watt? This is 2000 joules per second. What is power? Power and energy are not the same thing. Okay, power is energy per unit time. So if I want to use energy, I have to have power times time. Okay, so Zelia, what's on the left side?
2000 times 8. Yeah, 2000 times 3.2.
Very good. And from here, you can find what this is. Those of you that did it, what's the answer? D. Okay. I will trust Kieran's answer. Is it not D? Oh, it's D. John? D. Cheryl? Not D. Oh, you didn't get it. Okay. A? Hey, what the fuck? Walao, eh?
No, 8. No, it's not.
Oh, it's definitely not A. Okay.
It's D.
Okay, it's D. Are we okay with this?
Yes, we are.
Yes, we are. Okay, good. Question 10. Can I have your answers? C. A lot of C. C? Oh, you haven't yet. Cheryl? Haven't do. Don't know. You got A, the two of you? C also. Okay, let's see. Okay, I put square. I don't know whether that's square. Okay, wait, what do you all do? You all do half times 600,000 times 100 square.
Yeah, I think it's A.
Okay, that is not C.
I think it's A.
Why? Huh? What's that? This is in kilometers per hour.
Wow.
Kinetic energy, when you use half mv square,
Oh.
this guy should be kg, yes. What unit should your velocity be in?
Meter per second.
Meter per second. So, how to convert? Okay. How to convert km per hour to meter per second? One at a time. Convert one at a time. Convert one at a time. Okay. So 100 becomes 100,000 meters per hour. What's next? Yeah, hour to second. 3,600 over 3,600. What's this value? 27.777. I can add a few more. Then you use this value here. What's your actual kinetic energy magnitude? Remember guys, when we're using joules or watts, as long as we're using SI units, everybody should be in SI units. That includes your velocity. Oh, okay. Half times 600,000 times 27.777 squared. Yes. Okay. Are we okay with this? This is not recording.
No.
Is it pointing towards the screen?
Yes.
Should be pointing towards the screen. Are we okay with this?
Yes.
If you confuse, better ask now. Okay, I give you all some time. Those who do not need the time, start doing question 11. You will need a protractor. Hold on, let's go. Okay, just give me out. Just give me out. I'm not saying anything. I'm not even here. Wait. Naomi, what's the principle of moments? Okay, wait. I write this down. For an object in equilibrium, okay, yes, the sum of your clockwise and anti-clockwise moments equal good. Clockwise moments and anti-clockwise moment moments are equal about the same figure. Good. Okay, by taking moments about point A determine tension. Cheryl, how to do this? Huh? You don't know? If this is your pivot, okay, I'm taking moments about him, right? Your 148 newtons, what's your perpendicular distance for 148 newtons? You draw a line, you're taking down, and you tell me which distance forms a 90-degree angle with that force. Huh? 0.26 exactly. So, okay, by principle of moments, okay, your ACW anti-clockwise equals to clockwise moment. What is your anti-clockwise moment, guys? Your anti-clockwise moment is from this fellow. Correct? He makes him go this way. True. Okay, so your tension times 0.74 equals to 148 times 0.26. Okay, and some of you guys have already calculated this. 52 newtons. Do you guys manage to get it?
Yeah.
Not the 12 of you. 12 of you are not going to get it. The two behind? Why? What do you do? I thought you are the one who already tell me 0.74. Oh, you just didn't finish it. Okay. Next, the third resultant force. Okay, so how we draw these guys? Okay, resultant means what? Means from start to end. What the fuck does start to end mean? Okay, so I'm going to start at a random point. Wait. Chill. Okay, so start to end, I will just start at a random point here. Okay, I'm going to draw forces of T and my weight of 148 newtons. Okay, before that I need a scale vector diagram. So, because in other words, I cannot draw like 52 cm and 148 cm, but paper's not that big. So you have to set a scale, maybe 1 cm to 10 newtons, for example. What the hell is it? Okay, 1 cm to 10 newtons means what? Okay, the T first, T remember is 52 in this direction, correct or not? Okay, so I'm going to draw a line horizontally. Okay, I do not have a ruler on the fucking map obviously, but you guys have rulers, or you should have rulers anyway. That measures 5.2 cm. Because 1 cm represents 10 newtons, 52 newtons will be represented by 5.2 cm. However, we are not going to label this fella as 5.2 cm. No. The measurement is only for our drawing's benefit. Okay? The actual value is what we put in, 52 newtons. Okay, that one is going horizontal. Then you have a vertical force going downwards with a value of what? Yes. 148. So how long should the line be? 14.8 cm down. Okay, it's going to be a long ass one. Okay, I don't have a ruler. You guys have, please use it. 148 meters. Okay, T is acting horizontally, weight is acting vertically. So you have a right angle here. Following so far? Okay, we are not done now, guys. This is a scale diagram for tension and weight. We still do not have our resultant force. That's why I'm going to refer back to this. Start to end. Where was my start point? My start point was here. Your end point is here. So your resultant, you're going to draw a line from your start to your end. This is your resultant force. Resultant, the final. Okay. Sometimes it may not have what to use. Yes, the arrow, if it's resultant force, it's from start to end. Are we clear? Okay. If we are clear, okay, what's the magnitude of the resultant force? It's not calculated. It's not in the question. You have to use your diagram.
1.7.
Are you kidding?
Not what?
Okay, make use of your skills.
Same scale.
What you do is you take your ruler. You got a 5.2 and 14.8, right? You take your ruler and measure how long this is. How long is it? Your forces it's like this, that it's a sequence. One then the other, not both at the same time. 15.8, okay, 15.8 cm. Which means it's how much? What's the force? Huh? 158 meters.
Wait, mine is like 55 times.
Okay, most of the time for these kind of questions, the range in the cm range is plus minus 0.1. It's not that big. Okay, and I don't have the model answer, but I'm sure it's about 15.7, 15.8. Okay?
Wait, then if you like, then how much will it be? Like, accuracy.
In the exam, you give as accurate as possible, right?
You are given by 6.
You won't know the actual answer. So you do as accurate as you can, and then you see.
But the range is you find by like finding the
Yes. So if you go and use Pythagoras theorem, right, and the working is like this, I say for example r equals to square root 52 squared plus 148 square, you're gonna get 0. Because you're not supposed to use Pythagoras theorem. So what do? You use this to check if your answer makes sense. So you measure first, this is your actual answer. Then if you're insecure, you don't know whether you're correct or not, use Pythagoras theorem. If you guys calculate this, it should be very close to this value.
1 by 6.
Okay? Then you're good.
Wait, but if you join everything correctly, but then like our resultant force is a bit off, but then if you draw correctly, like,
If you draw everything correctly, your resultant force should not be off. Okay? What's the angle from vertical, guys? Go and take your protractor and go and measure. Okay, dotted line is your vertical. Go and measure this. Alternatively, if you don't know whether how do I know that this dotted line is vertical? Never mind. Measure your horizontal first, x. Then your answer will be 90 minus x to get your answer. Correct? Okay, it's the same angle though. Alternate angles. You see the Z.
Yeah.
Oh, okay, fine. Fair enough. Fair enough. Let's use the bottom one then. Okay, this one. Cheryl's angle? No. Don't use trigo. You don't have protractor. Is it like okay. Then I'll borrow. See the angle. Correct. Again, you can use that to check, but you cannot have overtaken. 20, so nice. Is it point something? Oh my god. Okay. But are we going to put point something? Yeah. 1 dp for angles, but it's always. No minus unnecessary bucks, guys. Next, on another occasion, the trapdoor is held open at a smaller angle. Compare magnitude of tension T to your rope. To your answer in part B, part 1. Now, this fella is a smaller angle. What do you think happens to tension? Think of it as a sequence. Okay, bigger. Why bigger? If you use lower angle, then
the tension will be more.
what?
Because like you easily topple. The tension you put
Oh, not about toppling. Okay, explain to me in terms of the values that you see here. Okay, just now your tension is based on 148 times 0.26 divided by 0.74. Correct? That's what we did, to get 52. However,
is it okay low? Lower line.
when this goes down, yes, 0.74 decreases. But that's not the only effect. What's another effect? Your 0.26 increases. Can you guys see? If this door is stretched a little bit more, your 140 shifts this way. But the 140 is still 140, so perpendicular distance here increase, down here decrease. Tension will increase.
I2
Okay, so how are you gonna say? Compare, so we just say magnitude increases. Why does magnitude increase? This is because the clockwise moment provided by the weight of the door. Clockwise moment provided by the weight of the door increases. Hence, T must increase to what we call maintain equilibrium.
Wait, why you put 20 and
Where's the
angle?
Oh fuck, sorry. Decrease.
Then you still put 1 dp.
Yep. Are we okay? Why? Okay, good. I will be skipping the next question because there's another drawing sheet. Okay? But I want you guys to do 13 and 14 together. Okay, 13 and 14 together. Whenever you guys are ready. I'll leave the answer for this one over here in case you haven't gotten to that. Okay, so why is the large force required to open the door? Okay, we will say that the pressure exerted by molecules on the outside of the door is high. Hence, the force exerted on the door is also very high, or it is also high. Since P equals to force per unit area. Yes, you can put in equations in your answer. Okay, then it is from here that we will say, therefore, a lot of force actually very high. Now here I will say force exerted on the door. Okay. Okay, relatively simpler example. Okay, yes, the actual answer will rely on suction, aka vacuum pressure, but we don't learn about that. Not yet. You go JC, you go JC. Okay? When the door of the refrigerator is open, it moves about the hinge. Handle is 0.8 meters. User exerts a force of 30 newtons. Well, this is easy. I think. But, how? Sherman? Agreed. It is moment equals to force times perpendicular distance, 30 times 0.8. To open, aka it is not here yet, it is closed. And with the point where it is closed, it is still 0.8. I'm opening the door. I'm providing a force of 30 newtons acting 0.8 meters away from the hinge. What? What's the confusion? Isn't it what? But your force is this way, not this way. If it was acting vertically, yeah, perpendicular to 0. But it's acting like that. So this is the perpendicular distance. Can you see? Line of action, perpendicular distance, 90 degrees. Okay? And this one will give you 24 Newton meters. Figure 13.1 also shows an instant that the door is closed, that the door is open. Discuss the effects on the moments after the door opens. it a shot. What do you think happens to the moment? Based on observation. Bear in mind your force is still constant, I'm still 30 newtons. Let's try. So at the start, this is your perpendicular distance, right? Now what's your perpendicular distance? Is it still 0.8? Higher or lower? Right? It's lower. Here. Now this one only. You don't have this part anymore. This part is what? Right? So now your perpendicular distance is this one, which obviously is less than 0.8. Right? Yes. Yes, what?
It's less than 0.8.
What is less than 0.8?
The new perpendicular distance. Wow.
Easy question. Okay, so obviously your moments will decrease because although force remains constant at 30 newtons, okay, force remains constant at 30 newtons, your perpendicular distance decreases. That's it. Easy, right? Not too difficult, right?
It's really cold.
As in this. It's okay, right? Okay, let's try. Don't worry. Okay, question 14, I don't know. Go. Yes. Okay, the projector there. Close. Okay guys, come. Let's go through. Firstly, I'm happy to see that everybody managed to draw a simple fucking graph. Straight line up from 3 to 9. Okay, calculate distance traveled, half times sum of parallel sides times height. Okay, it's just a simple trapezium. Half times 3 plus 9 times 3, 12, 3, 36, 18 meters. Okay, each of the
Oh, times half? I didn't know that.
Okay, now you do. Each of the 4 car tires has an area of 0.015. Exert a pressure of 200 kilopascal. Determine the weight of the car. Okay, so your weight, aka force, is equal to pressure times area. Everybody agree with me on this? John? Okay, pressure 200,000 Pascal, area 0.015 times 4 different tires, and you get your answer. 200, 0.06, it is the 12,000. Not 12,000? But if I times 4 here, then it doesn't matter. Pressure is force over area. That's it. answer 12,000 newtons.
Not the 16,000.
Identify an action reaction pair. Okay, this one, if you don't know, means your school didn't teach it. And if your school didn't teach it and you have no idea what the fuck this is, let me explain it now. Okay? There is certain criteria to qualify as an action reaction pair. Do you know what it is? Don't know. There's 4 criteria. After I go through this, do not forget it. Okay? Number 1. Forces must be of equal magnitude. If I push you, I also feel the force. Okay, action reaction pair. Second criteria. Forces must be in opposite directions. Up to this point it's okay, right? Okay, relatively easy to understand, I think. Okay, equal magnitude, opposite directions. I realize I need a bit more space to shift them out a bit. Okay, your third criteria, forces must be on opposing or opposite bodies. What does this mean? Okay, essentially, right, your action reaction pair is about Newton's third law, which states that when A exerts a force on B, it is equal to the force that B exerts on A. Do you guys recognize this? Newton's third law. Okay? Your last one is the one that's perhaps the hardest for secondary school to understand. Okay, but I will help you guys out. Your forces must be of the same type. What is a type of force? Let's go through. Okay, what does type mean? Type, okay, we can split it up into 2 main categories. Contact forces, aka your normal force. What's normal force? Normal force is if I push against the wall. Why does my hand not sink into the wall? It's because the wall automatically exerts a normal force against my hand. Why is it that we are not sinking into the floor? We have weight now. Why are we not sinking down? It's because the floor automatically exerts a upward normal force on us. Understood? Okay, sometimes your school might call this normal reaction force. Sure. Okay, so your normal force, your normal reaction force, all these are here. Okay, another one, air resistance. Air resistance requires the air to come into contact with you. That is a contact force. Friction, another one. Okay? And of course, if one category is contact forces, then the other category will be no shit, next, good. Non-contact forces. But you know something stupid, I don't hear it yet. Okay, I don't hear it yet. Wait. Your non-contact forces, something like gravity, aka your weight. Weight is a non-contact force. Maybe magnetism. Right? All these non-contact ones, you don't have to touch them. Okay. Okay, for those of you who take, everybody here takes chem. All of your electrostatic force of attraction, electrostatic FOA, your intermolecular force of attraction, all of these non-contact attractive forces within different ions, cation and anion. One positive, one negative, they will attract what? Right? Yes, what? Faster, you have my attention, what? Okay, okay, so the only action reaction pair force that we can identify here is if I draw the car. Okay, you have your wheel and you have the floor. Your normal contact force is between here. If I zoom this fella out, okay, bottom of the wheel and your floor. Okay, you have the force of the wheel on the floor, and you have the force on the wheel by the floor. sorry. Force on the floor by the wheel and force on the wheel by the floor. Okay, so the top one is force by wheel on floor. The other one is force by floor on wheel. Understand? This is normal contact force. Okay? Here. Okay, so your action reaction pair, okay, let's identify it. Force, sorry, contact force of wheel on floor. Actually, is it floor or is it a road? Fuck. On road. And contact force on wheel. Let's use the same fucking words. Off road on wheel. Okay, one is wheel on road, the other is road on wheel. But they are equal. That's why your car doesn't sink or fly.
So what about like kinetic and friction? Because like
There is no kinetic force. There's only kinetic energy. Right? Friction, sure, but there is friction is, if you want to use friction, the pedal has to be moving.
it's not moving. It's moving like
Okay, yeah, actually that's true. But how your answer is you want to use friction, okay? Let me just voice it out first. Friction is possible. We will have to say friction on wheels by road and friction
on road by wheel.
exactly getting it now on road by wheels.
Wait, the top one is 12,000, right?
Yeah,
Not eh? No.
they ask for weight. Mass is 1,200 kg. Weight is the force. Yes.
Contact force is the same as normal.
Normal reaction force, contact force. Yes.
So why can't we walk on water?
We can't walk on water because okay, we can't. Let's understand why we can't walk on water. Firstly, water is unable to provide us with enough contact force, and the reason for that is because water molecules can slide, right? So the moment a force is exerted, the water molecules slide out of the way, and your foot goes through. But solid, everybody's stuck. So you apply force so that it will separate randomly.
So you have fast enough and
No, you can't. Why? You fucking watch like Flash or like Incredibles and shit, you see a current run across water. That's not fucking possible. The moment a force is exerted, the molecules go away and you will sink.
Wait, did Jesus walk on water?
Let's not bring religion into it, it sounds very complicated. Jesus did walk on water, but to be fair, Jesus isn't like one of us. He is ascended, you know? He's not bound by physical rules like us. All of us are like fucking noobs, okay? He is not such a noob. Okay, let's do question 15, guys. What? Okay, give this question a try. It's great. Let's go through the question. No? You wanna try? What? Hey, what? Say, tell me what happened. Okay, marathon is a long distance race of about 42 kilometers. Water on the skin of a 65 kg marathon runner evaporates as he runs. Level of dehydration, percentage loss of body mass. When the sweat evaporates, it cools down the marathon runner. Do you all know why? You know why? Naomi, you know why? Cheryl? Water vapor, no, it's not water vapor. You know why?
Because you use mass.
Why when you sweat, you feel cooler? Cause it's water. Yeah, so what if it's water? Not quite. Okay, so there's a reason why like, it's natural for people to sweat when it feels very warm. Okay, it's called thermal regulation. Now that's not important. Okay, the important thing is why does evaporation cause cooling? Okay, this is an exam question. Okay, and here's the answer. Alright? Sweat. Not okay, that's not sweat. Let's just say water on the surface of the skin. Okay, to evaporate, what do you need? You need to break free from the bonds that are holding you in liquid state, correct? Then you can escape as a gas, right? So water on the surface of the skin gains kinetic energy from your surrounding molecules and escapes. Okay, I gain to escape. I need to gain energy from people around me. Agree? So I gain. Everybody who's left behind after I fuck off has less energy. True. So we say that, okay, this is a keyword here, average KE of molecules decreases. So temperature goes down. This is legit, okay, this is actually what happens. There's a reason, like when you come out of the shower and your body is wet and you feel very cold. Why? It's because of this. Every time a single droplet evaporates, it absorbs heat from your skin. Then you feel very cold.
How does the water come out?
When you shower, how does the water come out?
When you sweat, where does the water come out?
Moisture from your skin. Your body. Moisture from your skin. Dude, just walk underneath. You're already underneath. Come out again. What the hell? Moisture. Give up. Okay. Moisture from your skin escapes in the form of sweat. That's why after you sweat fucking a lot, right, you find a restless because you lose water. And that's
Can we say that the skin is a partially permeable membrane?
Your skin by nature is already partially permeable. That's why our skin can absorb and whatever. But that's not something that will come out, although it's an interesting concept. Okay, let's go through. So average loss of energy per hour is 2.3 times 10 power 6 mass that evaporated. Latent of vaporization, 2.4 10 power 6. We are going to use this formula. Change in state, right? Evaporation is liquid to gas. Did we do it? Yes. What's the formula? This one? What formula will you use? I just said it. Which one? Good guess. No. Naomi? What's the third one? M times L. Which L am I using? As in, okay, yeah, sure. Here we are going to use later your vaporization. Because sweat, evaporation is liquid to fucking gas. We are not going to use fusion. Okay? Your Q, energy loss, 2.3 times 10 power 6. Mass is 2.4, sorry, mass is an unknown. Mass is an unknown. Latent of vaporization, 2.4 times 10 power 6. Jaden, what's the mass of water that I lose? 0.958 what? kg.
How do you lose 900 grams of water?
That's not a lot. 1 hour of running now. Have you read for 1 hour before? You said fucking a lot. If you run properly. If you like scroll to everything. Okay? As the runner runs, his body's average production of thermal energy is that. Assuming that he only loses energy by evaporation, calculate rise in temperature. Oh, this question is difficult. This question is really interesting. So, you have 3.2 times 10 power 6 joules. Correct? Yes, yes. Okay. Now, energy lost by evaporation is this. Energy production is this. So how much energy, if you produce a certain amount of energy, that energy can be used for two different things. Number one is evaporate your sweat. Number two is increase temperature of your body.
Does it calculate a percentage?
Not percentage. So, in other words, what I'm trying to say, right? Let's explain in a fucking primary school model, okay? This total value of energy production is 3.2 times 10 power 6 joules. Okay? One part of this 3.2 times 10 power 6 is to evaporate your sweat. Kara, what's the other part used for?
What?
What's the other part used for?
The ones stay on your body.
The sweat that stays on your body. What? No lah. Okay. I lose energy by evaporation. The other component, of course, is increased temperature of body. Your energy production cannot all go to sweat, mah. Some of it will have to heat up your body. Okay, so when this happens, we are going to calculate 3.2 times 10 power 6. Okay, equals to your energy used to evaporate the sweat. We calculated this one just now. 2.3 times 10 power 6 joules. John, what else? Shush. Last one. I tell you, ask you. Okay, what's this? This is your energy production, right? Your energy production is used for what? What's this 2.3 times 10 power 6?
Average loss of energy from evaporation from the steam.
So this 2.3 times 10 power 6 is your sweat evaporation. So what's over here?
Temperature of the body.
Is to increase temperature of the body. How to calculate?
I don't know, I sleep.
Okay, let me do it together. Hey, chill bro. Just do it together again, man. Why you going to put here?
I really fun.
Huh? 0.9. What's 0.9? This one?
No, like the temperature one.
Oh, as in you calculate the value, is it? Okay, sure. So down here will be the energy to increase temperature. Okay, so let's calculate that. Energy to increase temperature is 0.9 times 10 power 6 joules. Okay, John, back to you. What? Increase temperature. When there's a change in temperature, what formula will we use?
Q equals to
So, what I will on the left side?
left side.
Yeah. I cannot just use this one. You are trying to find out rise in temperature. AKA, this is your delta T. Your delta T should be your unknown. The rest of you stop waiting for answer and do yourself.
Minus what?
Minus what? I already minus, bro.
Oh.
How you get? What's 0.9?
65 times.
65?
Times 3500 times. So, temperature.
Yes.
Yeah.
Why take so long? What's your delta T?
Three point nine.
3.956. Okay. So 3.96 degrees Celsius. Every hour increase by 3.96. This fella's thermal regulation is disgustingly bad. Probably not a very safe guy. Are we okay? MC delta T. The first one. Because they gave us specific capacity, I cannot use the bottom one. I don't have heat capacity, I have specific. Copy? Yeah, you will use that formula. Yes. Can we pause for a second? So if there is no increase in the runner's body temperature, guys, that means that this thing is non-existent now. Correct or not? But there is another component that fits this criteria. That other component will now be my breathing. So that means my 3.2 times 10 power 6 is equivalent to evaporation from skin plus your water vapor lost with breathing. Let's just use evaporation when breathing. Okay, and it is from here that I can calculate, I have 3.2 times 10 power 6 equals to, what's evaporation from skin? What? 2.3 times 10 power 6, plus your evaporation from breathing, evaporation when breathing. So your evaporation from breathing will be your 0.9 that you will see just now. But now, instead of increase in temperature, this energy is used to vaporize your water vapor inside the lungs. So I have mass times 2.4 times 10 power 6 to give you 0.9 times 10 power 6. What's the mass?
Wait.
Anyone? 0.375, okay? kg. But this 0.375 kg is per hour. All of these so far has been per hour. So in 4 hours, you will have lost 1.5 kg of water. we take away the evaporation from skin, so the only thing that's left behind, now that my body temperature is assumed to be constant, is the breathing part. The water vapor inside the lungs getting vaporized. Yeah.
Then the formula is like
Which one?
F times C.
Yes. Vaporization. Okay, so using your answer, determine the mass of water that the runner should consume in order to keep him at the lower end of moderate dehydration. What is lower end of moderate dehydration? 3%.
Isn't it 3 point something? 3 point something. Lower end of moderate.
Okay, I mean lower end will be either 3 or 5. But is it 3 or 5?
No, below 3.
Below 3. Below 3, then you are not very dehydrated.
Oh wait, so isn't it 5%?
Lower end of moderate dehydration is the answer. Okay? So if you are lower end of moderate dehydration, we are actually looking at 3, not 5. Okay, I'm not so dehydrated. I only lost 3% of it. 3% of water. Wait. Sorry. It's 5.
That's what I thought.
Okay? Now, I misunderstood what you meant by lower end. Okay, lower end is
It's like
not
it was
a,
severe.
yeah, it's not a good thing. I'm almost into severe. I'm not yet severe dehydration. I'm
Who's
5%.
playing with the word?
Who's playing the words? No, it's just me having a shitty English bro.
That's what Chinese is.
What? A lot of people disagree with you. Okay, so anyway, determine the mass of water that I should consume during the 4-hour race so I am kept at the lower end of moderate dehydration. How?
Define that means,
Okay, so mass of water lost, okay, per hour. Can somebody give me this value?
1.5.
0.375 is not the full answer.
0.375 plus 0.158.
Very good. Okay, 0.375 plus 0.958. What's the answer? How did I get 0.1958? Okay, mass of water lost includes water vapor in the lungs as well as the skin. I have to include both. 1.333. So nice number.
Yeah.
Okay.
No, because it's like, it's 0.958.
But
Okay.
okay.
It's just a short answer.
Sure. Okay, so I am using 1.333 kg per hour. Question. What is the percentage loss in 4 hours? You 1.333 kg per hour, right? You times 4 hours is the total amount of water you are going to be losing. Kg, what's the value?
5.3.
Kg. Cool. What's my next step? Okay. Huh? You don't know? Didn't? Okay, so now 5.332 kilograms is how much I'm losing. Right now? Okay, what's the percentage out of my body mass in water? Remember, I'm not supposed to go below 5. What percentage is this? 8.2. Okay, yeah, that's the answer I got. So. Okay, percentage by body mass. Sorry, of body mass. 5.332. Naomi, what's your body weight? Not your body weight, the answer is body weight. The question is body weight. So what percentage of water am I losing? So you go, let's have this answer. Not yet, not. 0 point. Percentage, percentage. Okay, 8.203%. I'm supposed to be 5%, which means I have a need to drink your 3.203%. What's the mass? Okay? What's the mass of water I require to drink so that I'm kept at a 5% body mass loss?
Where did that 3.203% come from?
This is how much I'm losing, right? I'm only supposed to lose 5. Which means I need to replenish this much. How? Yeah, in kg will be 2.07. How do you get 2.07? Wait, it's in my answer is very close, but it's not 2.07. How do you get? Do you use 3.203? Then you divide by what? Or what do you do with the 3.203? You're confused. Your mass is 65 kg. Total mass. Yes. Yes. Yeah, what's that? Okay, so the mass that you need to drink is 3.203% of 65 kg, which is 2.08195. Okay, round up, that's 2.08 kg of water. AKA, you just got to drink like 2 big ass bottles before the race.
Only the stitches, what?
I mean, if you drink it properly, like it sips really quickly, it's just like it doesn't pull up the cup.
Oh.
Okay, difficult question, guys. Not so easy, but I think it's safe to say that this will be probably what you guys are expecting in your NLP. Okay.
Why?